Out of every mission humanity has ever launched toward Mars, roughly 60% have failed. Reaching the red planet requires overcoming a gauntlet of extreme physics and statistical anomalies. The first barrier is Earth's own gravity. Escaping it requires a vehicle to reach speeds near 20,000 kilometers per hour. To generate that much thrust, engineers combine liquid propellants for sustained, controlled burns, with solid rocket boosters delivering brute force chemical reactions right off the pad. It is a common assumption that a rocket's job is simply to fly straight up into the void. But if a rocket only moved vertically, gravity would eventually pull it right back down to the launch pad the moment its fuel tanks ran dry. This demonstrates the gravity turn. After liftoff, the rocket actively tilts, using Earth's gravitational pull to naturally curve its flight path. Instead of fighting gravity purely with fuel, the vehicle redirects its energy. The objective switches from gaining altitude to building immense lateral speed. Achieving orbit is a matter of sideways acceleration. The vehicle must move horizontally so fast that as it falls back toward Earth, it continuously misses the ground. Once in orbit, the next problem is navigation. Earth and Mars are moving targets, traveling around the Sun at entirely different speeds. Pointing a rocket at Mars and firing in a straight line guarantees a miss. This diagram shows the mathematical solution to that problem, the Hohmann transfer orbit. It is an elliptical orbit designed to efficiently move a spacecraft between two circular orbits of different altitudes. Executing this maneuver requires precise timing, known as a launch window. Engineers initiate a specific engine burn to push the spacecraft off Earth's orbital path and onto this expanding elliptical arc. From there, the spacecraft mostly coasts, timed perfectly to arrive exactly where Mars will be months in the future.
Interplanetary travel rarely involves engines blazing across the blackness of space. It relies on precise mathematical coasting along invisible elliptical highways. The coasting ends violently. The spacecraft hits the top of the Martian atmosphere, traveling nearly 20,000 kilometers per hour. In seconds, atmospheric friction superheats the protective heat shield to thousands of degrees. At this exact moment, Earth is tens of millions of kilometers away. Radio signals, traveling at the absolute speed of light, take over 11 minutes to cross that distance. The entire descent from the top of the atmosphere to the dirt takes about 7 minutes. This creates a terrifying reality for mission control. By the time they confirm atmospheric entry, the rover has been on the ground for 4 minutes. The vehicle must execute the entire entry, descent, and landing sequence entirely on its own. Onboard computers independently fire stabilizing thrusters, deploy supersonic parachutes, and scan the approaching ground for hazards. The sequence culminates in the sky crane maneuver. A rocket-powered descent stage hovers, gently lowering the rover to the surface on nylon cables. No human hand guided that touchdown. A series of autonomous, pre-programmed robotic reflexes brought the machine safely to the dust. The vehicle survived. Now it has to phone home. Sending complex scientific data across millions of kilometers of deep space requires specialized communications infrastructure. NASA listens for these transmissions using the Deep Space Network, a global array of massive radio dishes like these at the Goldstone complex. They are sensitive enough to detect a signal from deep space that is as faint as a billionth of a watt. Standard internet protocols on Earth assume continuous, high-speed connections with negligible delays.
If you try to run that same system across the solar system, where planets block signals and light speed lag stretches into minutes, the connection instantly fails. This diagram illustrates the solution: delay-tolerant networking, powered by the bundle protocol. Instead of demanding a continuous link, the rover packages its data into bundles. It sends them up to a Mars orbiter passing overhead, which stores them, and then forwards them to Earth the moment a clear radio path opens up. Landing a rover on Mars requires an entirely new internet architecture spanning the solar system. When that transmission hits servers on Earth, it doesn't instantly look like a beautiful Martian landscape. The raw digital files are flat, often containing severe exposure imbalances and white balance errors from the harsh alien lighting conditions. To fix this, imaging teams apply rigorous color grading. Filmmakers often use grading for artistic stylization, but scientists use these tools to correct the raw footage. They meticulously balance the hues and adjust the contrast to represent the true, accurate lighting of the Martian environment. The result is this: a crisp, authentic, human-readable window into an alien world. Next time you pull out your phone and look at a picture of the Martian surface, remember the physical realities it took to capture it. You are looking at the culmination of controlled rocket fire, orbital geometry, automated terror, and interplanetary data routing.